So if you recall, way back when we were doing latches, we designed an edge detector that was just a purely combinational circuit that took advantage of this phenomenon of propagation delay. And now we're going to revisit the edge detector, but we're going to revisit it as a state machine. So what this state machine is going to do is it is going to detect when an incoming input signal, X, which is a single bit, transitions from either 0 to 1 or from 1 to 0. And we are going to design this in two ways. We're going to design it firstly as a Moore machine and secondly as a Mealy machine. So the first thing to note is that an edge detector is like a sequence detector, which we have done before, except in this case we're detecting two sequences, 0, 1 and 1, 0. So the Moore design is going to look like this. I'm going to have a start or idle state. And again, unless I have detected one of the two sequences that I am looking for, my output is always going to be 0. So like a sequence detector, I'm going to output high when either 0, 1 or 1, 0 has been detected. And in all other cases, I am going to output a 0. So the state machine looks like this. I have a start state, again, outputting 0. And I have two options here. So either I can detect my incoming bit stream. So again, I have a single bit, which is X, and a single output, which is Y. X is my incoming bit stream. And I'm going to detect when it transitions either from 0 to 1 or from 1 to 0. I am going to output 0 under all circumstances unless I have detected those specified transitions. So in the first case, my X incoming bit is a 0, and I'm going to move to a state that I'm going to call just 0. And again, I'm still going to output 0 because I haven't detected any transition yet. My second option, again, starting from the start state, is that I've detected a 1. So I'm putting them in double quotes to indicate that this is not the binary value that I'm assigning to my state, but rather this indicates that a 1 has been detected. So if my incoming bit is a 1, then I will move to this state that I'm calling 1 detected. So 1 has been detected in this state. Okay, now from here, I can have two options. Okay, so I'm going to start here at the 0 detected state, and I have two options here. So the first option is that I detect another 0. And if I detect another 0, I'm just going to stay in the same state. I haven't gotten anywhere. But if I detect a 1, then I'm going to move to this state that I call 0, 1. A 0, 1 transition has been detected, and in this state, I'm going to output a 1. So if from this state where a 0 has been detected, if another 0 has been detected, then I will remain in the same state. But if a 1 is detected, then I have just had a transition from 0 to 1. I move to a new state that I'm just labeling as 0, 1, and I'm going to output a high because now I have just detected my 0, 1 transition. Similarly, over here, in my 1 detected state over here, so if another 1 has been detected, then I'm just going to remain in that same state, saying that a 1 has been detected. But if a 0 has been detected, then I'm going to move into another state that is called 1, 0 has been detected. That's my label for it. I'm going to output high because it tells me that the sequence that I'm looking for, a 1 followed by a 0, has been detected. So I will move to this state in the case where x equal to 0. So remember that I was in the state where a 1 was detected, and then a 0 comes in. My incoming bit stream is now 0. And I moved to this state where a 1 and 0 have been detected one after the other. Great. Okay, so where do I move from here? So two things can happen. So let's look at this state over here. Now again, I'm in this state. Two things can happen. I can detect a 0, or I can detect another 1. Okay, so easy enough. If I detect a 0, then the last 2 bits I have detected were a 1 followed by a 0, right? Because I'm in this state. Remember, the incoming bit stream at this point was I got a 0, then I got a 1, and now I'm getting another 0. So that is a 1-0 transition. So if I get a 0, I should be moving to this state. And if I get another 1, then a 1 has been detected, and I should move to this state. I'm not going to output, again, I should not be outputting a high here. I'm just going to be outputting a 0 as shown in this state. So I'm outputting a 0 because I have a 1 followed by another 1. And it's the same logic over here in this state where I have just detected in the last couple of clock cycles a 1 followed by a 0. If I get another 1, then I have my last 2 bits, bits in my bit stream were a 0 followed by a 1. So remember, because how did we get here? We got here because I got a 0. If I now get another 1, then the last 2 bits detected were 0 followed by 1. That's this state over here, and I should output a high because now I've just detected another low to high transition. So if that happens, then I will move to my 0-1 has been detected state and output a high. And similarly, if a 0 has been detected in this state, well, the last couple of bits I've received have been 0. So I'm going to move over here, and I'm going to label this x equal to 0. So this is my state transition diagram. How do I go about translating this now into a state table or excitation table? So the first thing I'm going to do is I'm going to just add some labels to my states. And as you can see, I have 5 unique states here. So I'm going to need 3 bits. And I'm just going to arbitrarily, this one, I'm going to call it 0, 0, 0. This one will be 0, 0, 1. This will be 0, 1, 0. This will be 0, 1, 1. And this will be 1, 0, 0. And again, how I choose to label them is fairly arbitrary as long as I am internally consistent in my design. So now I will go ahead. I'm not going to write the full excitation table for you, but at least I will show you how to do the state table. So let's do that. Okay, so I started drawing my state table, and again, a state table is just an excitation table without my control inputs, because I'm assuming you know how to do that already, but I want to get you started on the state table. So what I've shown you is over here, I have 3 bits to represent my present state, right? Because I need 3 bits to represent present state, that's these guys. Then I have an input X as well, because my transitions are conditional. So if you notice, my transitions are conditional on my input X, right? So depending on what state I'm in and what my input is, I will transition to a different next state. So my next state is dependent on basically 4 binary variables, the 3 bits that represent my present state and the bit that represents my input. So I am going to need 16 rows to represent all possible permutations of this. So let's write that. So I filled out my truth table, and I kind of like to put these dividers here after every 4 rows. Just makes it easier for me to keep track of. So I'm going to start on the first row over here. So all this says is if my present state is 0, 0, 0, 0, that's this over here, and my input x is 0, what's my next state going to be? And my next state, so again, I'm in state 0, 0, 0, my input x is 0, then I follow this transition over here, and my next state is going to be 0, 0, 1. So I'm just going to fill that out over here. Okay, next row, I'm in state 0, 0, 0, so again, that's my start state, and my input x is 1, so my next state is going to be 1, 0, 0. And I'm going to just fill this out for all the remaining. I'll just show you how this works for the first few. So if I'm in state 0, 0, 0, 1, that's this row over here, and my input x is 0, then my next state is also 0, 0, 0. Actually, that was 1 extra 0. 0, 0, 1. And if I'm in this state 0, 0, 1, and my input is 1, then I transition to this state, which I've labeled 0, 1, 0. Okay, and I'm going to move on to here. So if I'm in state 0, 1, 0, that's this guy over here. My input is 0. So my input is 0. What's my next state? 0, 1, 1. So again, the state transition diagram should have everything that I need to write not only my excitation table, and again, the state table is basically an excitation table, but without the control inputs, and also my output logic truth table, which in this case is very simple. So if I'm in state 0, 1, 0, that's this, and x is 0. Again, like I said, my next state is going to be 0, 1, 1, so I'm going to write that here. If, on the other hand, my input x is 1, I move to state 1, 0, 0. Okay, and from state 0, 1, 1, that's this. If my input is 0, then I move over here to state 0, 0, 1. Conversely, if my input is 1, then I am going to move over here to state 0, 1, 0. And only one state left to go. So if I'm in state 1, 0, 0, that's this, right? So I'm doing this row over here. Input x is 0. My next state is 0, 1, 1. But if my input x is 1, I remain in the same state. Back in 1, 0, 0. And there is no state 1, 0, 1, 1, 1, 0, or 1, 1, 1. So I just write a big fat X over here. And I'm going to leave these as don't cares. Even if when I do my excitation table and I do my control logic, I can just leave these as don't cares, provided that I have a means of setting my circuit back into the start state. So maybe that could be like an asynchronous clear or something like that. Some like asynchronous means of resetting my circuit back into this idle state or start state over here. So this is basically the state table, and the output logic truth table is also really simple. So my output logic truth table, before I start to write it, this is a Moore machine, and you can see that actually my outputs are entirely dependent on the present state. They have no dependency on the input X. The input X determines transition, so that affects the excitation table, or what I've done, which is the state table, which is just an excitation table with the control logic missing. So my transitions from state to state, represented by the arrows in my state transition diagram, those are determined by, firstly, what is the present state, what state am I in, and also what is my input X. But my outputs are dependent only on what state I'm in. This is a Moore machine. So I can see this here, right? Like if I look at every bubble, so every bubble is representing my present state. And if I look at every bubble, I can see that the output is wholly determined by what state I'm in. There's no other variable. So it's not dependent on the input. That's what makes this a Moore design. So when I draw my output logic truth table, all I need are my 8 rows representing all possible present states. Okay, so I filled out my output logic truth table, at least my present state, and I'm going to write what y is. So I'm not going to derive the Boolean expressions because I feel like you already know how to do it at this point. But let's just go over how do I fill out the output logic truth table. And from there, I mean, it's pretty straightforward on how to derive the Boolean logic expressions for y. So I've just arbitrarily named my input x and my output y. But y is basically the output that is high when a transition from 0 to 1 or 1, 0 has been detected. So my output, so again, I'm just straightforwardly following the state transition diagram. So in this state 0, 0, 0, 0, 0, 1, 1, 0, 0, in all those states, my output y is 0. And it's only in state 0, 1, 0 and 0, 1, 1, these guys over here, that my output is high, right? Because those are the states where a transition has been detected. And then my other 3 states, I'm just going to put x's here because actually I don't care because these are invalid states anyway. So that's it. Basically, I have completely done my Moore design. And now I want to do it as a Mealy machine and show you the difference. So the state transition diagram for the Mealy machine is going to start off very similarly. So I'm going to have like a start state. And in the start state, again, I'm going to output 0 because I'm only outputting a high when a transition, either 0, 1 or 1, 0 has been detected. Okay, so what I'm going to do here is I'm going to have 2 possibilities again. So like I start off very, very similarly where if my input x is 0, I'm going to transition to this state called, that I'm just going to label with like sort of a human-friendly name called 0 detected. I'm going to leave the outputs blank for now. And I'm going to label this transition. This transition is conditional. It's conditional on x. Here's symmetrically, let's start off the other way. So if I'm in the start state and I get an incoming 1, then I'm going to move to this state called a 1 has been detected. Okay, and now in the Mealy machine, that's it. There are no more states. How am I going to do this? So I'm going to show you how this works. Okay, so if I'm in the state where a 0 has been detected, okay, that's this state right here. If I'm in this state where a 0 has been detected and I get another 0, okay, then I am simply going to output 0, right? So if I get a 0, I'm going to output a 0. But if I get a 1, then it means that I've actually, my last 2 incoming bits have been 0 followed by a 1. So I'm going to output 1 at this point. And the other thing that I'm going to do is I'm going to transition over here to indicate that 1 was the last bit that I detected. Okay, so this is very subtly different from the way we did it as a Moore machine, and maybe like slightly counterintuitive because I not only have conditional outputs, but I also have conditional transitions. So let's do it again for this other state where a 1 has been detected. And again, I am only keeping track now of the last one bit that was incoming. So the last bit that was incoming, whereas before for the Mealy machine, for the Moore machine, I actually kept track of the last two bits. So I had a separate state for 0, 1 and another state for 1, 0. But in this case, I'm not doing that. I'm only keeping track of the last bit that was incoming. And what I'm going to do in this state over here, so again, I started off in this idle state and I got a 1. An incoming bit on the line was high. And I transitioned to this state that tells me that the last bit I received was a 1. So now what happens if I'm in this state where the last bit I received was a 1 and I get a 0? Well, in that case, the last two bits I've received were 1, 0. So that tells me that I have detected a transition and I need to output a high. Conversely, if I am in this state where a 1 was detected and I get another 1, then I'm just going to output nothing and I'm going to stay in this state. I'm going to remain in this state because this is the state for when the last bit I received was a 1. But what I didn't tell you is if I received, so I'm in this state where the last bit I received was a 1 and then I get a 0, then I need to transition back to this state because this is the state for the last bit that indicates that the last bit I received was a 0. And that's it. Like this, basically, I'm just going to be bouncing between these two states. So once I'm out of this start state, basically, like which is after I've initialized my whole circuit, like maybe I power on or whatever, I've initialized my circuit, and now I'm basically just bouncing between these two states. That's it. So again, I'm kind of separating out the state and the output. I'm sort of decoupling them in the sense that I have only two states now. The state only tracks what the last bit I received was. And then depending on the state I'm in, if I get, if I've detected a low to high or high to low transition, then I will output accordingly, either a 0 or 1. So 1 when a transition was detected. And I will transition if a transition was detected, then it means that I need to transition states as well at the next clock edge. So this is slightly more complex to wrap your head around, but it's also simpler because right now, as you can see, I only have 3 states as opposed to 5 before, and I can represent this whole thing with 2 bits. So I'll just call this 0, 1, and, I'll be consistent actually with what I did before. So I'll call this 0, 1, and I'll call this 1, 0. And I'm going to do my corresponding state table. So again, when I sit down to do my state table, what I need to remember is my transition. So again, the state table is there to tell me under what conditions I transition from state to state. And my transitions are conditional on what state I'm in. So what is my present state? They are still also conditional on my input X. So let's represent that. Okay, so I filled out my state table. Now it's only 8 rows as opposed to, recall that we had 16 rows for the Moore design, right? Why? Because I needed 3 bits to represent my present state as opposed to just 2 in the Mealy design. So, and again, my transitions are still conditional on my input X. So that hasn't changed, but I only have 2 bits to represent my present state. So my next state is dependent on the values of 3 binary variables, and I filled them out truth table form. And now I'm just going to write what the next state is in each case. So again, looking at state 0, 0, X is 0. My next state is going to be 0, 1. But when X is 1, my next state is going to be 1, 0. If I'm in state 0, 1, And, oops. So if I'm in state 0, 1, and my input, so again, I'm not looking at outputs here. I'm not looking at anything below the line, okay? I'm only looking at arrows, okay? So I'm in state 0, 1. My input is 0. And I realized that actually I forgot to fill that out here. So what I did not write was the transition to the same state. So let's write that here. So if I'm in one of these states where, if I'm in this state where the last incoming bit was a 0, and I get another 0, well, the last incoming bit was still 0, so I'm going to remain in the same state. And the same logic applies here. If I'm in this state where the last incoming bit, so again, the whole purpose of this state, the meaning of this state is the last incoming bit was 1, and if I get another 1, well, I'm just going to remain in the same state because my last incoming bit was still 1. So if I'm in state 0, 1, so that's the state over here, and I get a 0, I remain in the same state, which is 0, 1. But if I get a 1, then I'm going to transition to the next state, 1, 0, which indicates that the last incoming bit was a 1. So I'm going to write that here, 1, 0. Similarly, if I am in state 1, 0, that's this, and I get a 0, the next state that I'm going to be in is 0, 1 to indicate that the last incoming bit was a 0. If I'm in state 1, 0 and I have a 1 incoming, my next state is going to remain state 1, 0. And these are X's because this is an invalid state. So these are my don't care conditions over here. And that's it. And now let's use this to also build the output logic truth table. So when we sit down to do the output logic truth table, I mean, I've already filled this in, so I've kind of given the game away, but you can see that as opposed to in the Moore model, which was over here, so in the Moore model, my output was dependent only on my present state. Now, I also had 8 rows simply because my present state was represented by 3 binary variables. And here, my output, as you can see, it is not enough to know what state I'm in to know what the output is. I not only need to know the output, but I need to know, I not only need to know what the present state is, I need to know what my input is because my output will vary within the same state. For a given state, my output will be different depending on if my input X is 0 or 1, at least for these 2 states. So that's why when I write my output logic truth table, I now have 3 columns. So I have 2 bits for my present state and my input. So they all have to be represented here. And then after that, it's pretty easy to fill out, right? So again, regardless of what my input is, if I'm in the start state, my output is going to be 0. And if I am in this 0, 1 state, so if X is 0, then I'm going to output 0. But if X is 1, then a transition has been detected and I'm outputting 1. And again, I don't even have to retain a sense of what this means. I just have to mindlessly follow my state transition diagram. So if you get the state transition diagram right, everything else follows. After that, it's just mindless transcribing from the state transition diagram to my excitation table and then from there to my output logic truth table. So really getting the state transition diagram, that is the hardest part, and that is the most critical part, in my opinion. So moving on to this state 1, 0, that's this state over here. Now, if X is 0, I'm going to output 1. And if X is 1, I'm outputting 0. And I do not have a state 1, 1. So that's what these rows are, right? And so I'm just going to put X's here. And then deriving the Boolean logic expression is pretty trivial after that. Now, the one thing that I haven't done is the block diagrams. And I'm going to do them both side by side just so that you can have a sense of what the difference is between the Moore machine and the Mealy machine. So let's go ahead and do those. So let's do the block diagram for the Moore model first and then the Mealy model. So as always, I mean, in any block diagram, the first thing I'm going to draw is the state memory block. This is not going to change between Moore model and Mealy model. This is simply an artifact of being a state machine. So I'm going to have my state memory and I'm going to have control logic, right? So the control logic is the stuff that gets me from the present state to the next state. That's what the control logic is. So if I'm using, let's say, JK flip-flops, it's all that combinational circuitry that is an input to or wired to my J's and K's for all my flip-flops. So that's control logic. Okay, so now that I have this, and these are common, by the way, to both Mealy and Moore. So I'm just going to copy it over here. And So what I'm going to do is in the Moore model, so recall that actually coming out of my state memory, I had 3 flip-flops, so therefore I had 3 cues. And actually, before I do this, let me just show another commonality. So there's the clock input, right? So the state memory is composed of flip-flops. So it's just a fancy way of saying flip-flops because the flip-flops, what they're doing in this context is they're keeping track of what state I'm in, okay? And they are the only sequential logic elements in my whole design. So they're the only guys that have a clock, okay, that are clocked. Everything else is combinational. My control logic is combinational, meaning it's just like logic gates, right? The state memory is not. The state memory is clocked. These are sequential logic elements. The other thing that I have in both actually, so maybe I copied this over too quickly, but I do have output logic in both, okay? And the output logic in both is simply my Y, if you'll recall. So I had like a single output, which was I just called it Y very unoriginally. And that was the guy that told me if I had that was the guy that told me if I was detecting either a 0-1 transition or a 1-0 transition. So it was high if I was and low if I wasn't. So, so now what I'm going to do is I'm going to show, so I'm starting with like the simplest stuff, and I'm actually just going to do it for both because why not? So my state memory, recall that for the Moore model, I needed 3 flip-flops. So I had 3 Q outputs, and I needed 3 flip-flops to represent the 3 bits for my state. So I had 5 states, therefore I need 3 bits to represent 5 states. And I need 3 flip-flops per, like 1 flip-flop per bit. So I need 3 flip-flops to represent all 3 bits. So I am going to write 3 arrows here that represent my, I'm just going to write them below because I don't want things to get messy. But basically I had Q2, Q1, and Q0 coming out of my state memory, going to my output logic. Simultaneously, they also went to my control logic. Okay, what's the equivalent over here in the Mealy model? So remember that I only needed 2 flip-flops actually. Like I only had 3 states. I had 2 fewer states than I had in the Moore model. So I only had Q1 and Q0. They were inputs to my output logic, sure, but they were also inputs to my control logic block. So remember, the control logic block is the guy that takes in the present state. These are the present states. They represent what is my present state, what's my state currently, okay? They are inputs to my control logic block. the idea behind the control logic is simply then to spit out all the, so again, I didn't specify here whether I was using J's or K's, JKs, or D flip-flops, or like there are other kinds of flip-flops. You could use SR or T or whatever, but I did not specify. So what I'm going to do is I'm just going to draw a line with a bar through it, indicating this is bust. What does bust mean? It's just fancy for saying that actually this is a bundle of wires. So I have like multiple outputs coming from my control logic block. So these represent my JKs or Ds, like depending on what I'm using. I'm going to say JKs or Ds. We know that there are other kinds of flip-flops, but these are the ones that we've been using in so far all along. So I'm just going to stick to that. So I've got my, so far everything looks pretty much the same between the mealy and more, except that I have 3 Qs in more and 2 Qs in the mealy. Like I only have 2 flip-flops in my mealy. So there's something else that's common to both. So the other thing that's common to both is that my next state depended on, first of all, what my present state was, but also on what my input was. And that was true of both. So how that affects, so again, I didn't go through the whole process, but hopefully you can extrapolate from what we've learned so far, which is that if I went to the trouble of writing out my Boolean expressions for my control logic, so again, these are like the JKs or Ds, like the control inputs to my flip-flops. So, and again, they're the control inputs that are needed to get me to the next state, right? So, they are based on, like this control logic is based on, and you'll see the if I had gone to the trouble of writing out a full excitation table instead of just a state table, and I had derived the Boolean logic expressions for my control logic, I would see that they were dependent on the present state. So my Qs coming from my flip-flops, coming from my state memory, basically, right? These guys. But they were also dependent, in both cases, they were also dependent on X. So I am going to put an arrow here. And how do I know this? So let me just show you. Well, let's go revisit this. So if I come back, this was my state table for the Moore design. Okay, and if I look at the state table for, and I don't even have to look at the state table actually, I just have to look at the state transition diagram. If I look at the state transition diagram, what I'm looking at now are the transitions, right? So the transitions, so remember that the control logic is there to get the correct transition from present state to next state. And my transitions are dependent on, so they are conditional. They're conditional on X. So what state I'm going to go to, what is my next state? If I'm in, let's say, for example, the start state, what next state I'm going to, right, whether I'm going here or here, is conditional on, first of all, what state I'm in, and also what my inputs are. And that was reflected in my state table, which again, you would have done an excitation table if you were seeking to implement this as a schematic, right? Or like a full circuit. So, so that's where this comes into play. That is what this X is, okay? And similarly, going back to the Mealy machine, I can also see that my transition to the next state, so what state I'm going to go to depends on, well, first of all, what state am I in now? That's my present state. And then also what's my input X? Because again, my transitions are conditional. They're conditional. So that's where it comes into play in the state table, right? So I need you to get this all straight in your head. So that's why I have X as an input to my control logic in both, right? So it's not just in the Moore model, in the Mealy model as well. But what distinguishes the Mealy from the Moore is in the Moore model, I'm done here. Like this is my final block diagram. There's nothing left to add. If you remember, the output logic was dependent only on my present state. I didn't care, and you can see this from the output logic truth table, but I can also see this from my state transition diagram, where now I'm looking inside the bubbles, right? And I'm looking at my outputs, and I see that I don't have any outputs that are conditional on my input. They're only dependent on what state I'm in. If I know what state I'm in, that is sufficient information to tell me what my output should be. But in the Mealy model, that was not the case. So going back to the Mealy model, this is what we just did. And we saw that actually the output, I can see this from, first of all, my output logic truth table, but if we want to go back further, where did this come from? This came from the state transition diagram. If I look at the state transition diagram, I see that at least in these two states, 0, 1, and 1, 0, which actually have a semantic meaning, which is basically 0 was the last bit detected and 1 was the last bit detected. I can see that the output is going to be dependent on what the value of the input was. So that's where I get this. So now I have one thing to add, which is I need to show that in my Mealy model, the output logic is dependent on, yes, my present state, but also what my input X is. And it's the presence of this that makes it a Mealy machine, not the presence or absence of this. So I can have conditional transitions, right? That's what this represents. This represents transitions that are conditional on my input X. But what this is outputs that are conditional on my input X. And I don't have that here, but I have that here. And this is a good example to see the distinctions between Moore and Mealy, because yes, so I do have a input X to my output logic, right? The other difference though is that in the Moore model, I have more states. That means that I will have more complex control logic. In the Mealy model, I have fewer states. I only have I have 3 states as opposed to 5 in the Moore machine, which made a difference for me in terms of the number of flip-flops that I required. So 2 instead of 3 in the Moore machine model. And so this is sort of like a good example to see the distinctions. Now, there is a way, if you're wondering if there's like a formula to go between one or the other. I mean, yes, but the point of this is just to show you the distinctions. What is the difference between the two? And I can see this here if I do a side-by-side comparison of the block diagram. Now, I don't want you to memorize this. You should understand where all of these come from and what the purpose of all this is and how to identify them on a schematic and where to find them in your state transition diagram. And basically, as I go through the design process, what is tied to what. So for example, when I'm designing my state table or my excitation table, what I'm looking at are the arrows in my state transition diagram, the transitions, right? And what I'm trying to derive from my excitation table is this guy, the control logic. That's the purpose of the excitation table. The output logic truth table, that's this, okay? So, and they're all these two blocks, control logic block and output logic block, are purely combinational. So I just need you to understand the relationships between these things and how they tie into each other as you're going through the design phase and how they tie into the state transition diagram. And also the distinctions between the Moore and the Mealy model. And this is a nice example. This is actually a very useful example as well in order to detect transitions. So this is it. This is your block diagram.